Before I jump into page 31, I definitely want to acknowledge this note about vocabulary at the bottom of page 30, just so that way when I start using some of this verbiage, it's not super confusing. The Riemann sum generally is just a way of saying, hey, I'm using rectangles to estimate an area. We don't always specify right Riemann sum or left Riemann sum, but usually you'll hear that phrasing if somebody chooses to do only one type of rectangle. Some questions require you to do both types of rectangles. Some will specify just use a left Riemann sum or only use a right Riemann sum. So you'll have to start getting used to reading the question for that information, because that will dictate which corner you use when you are actually making your shapes in your diagrams. Some textbooks also abbreviate the left rectangular approximation method, or LRAM, and the right rectangular approximation method, called RRAM, and that's basically synonymous with Riemann sums, just without the name dropping. So you'll definitely see all of those phrases kind of intermixed throughout this packet. I believe the AP test uses the phrase Riemann sum specifically. They use the guy's name, but some textbook publishers and some college professors stick with LRAM and RRAM. So just be advised that those things are all interchangeable. It's not really a big idea. It's just something that's worth noting in case you hear that verbiage being used a little bit more loosely. Now on page 31, the goal is to try, if we can, to acknowledge the inherent reality that neither of the methods that you used, left or right Riemann sums, were particularly accurate. We know that they were getting closer if we got a more narrow rectangle into each diagram. But as we've mentioned in the past, the trade-off is it really does make the area so much more tedious. And doing 8 rectangles, which involved using decimals, definitely started to borderline on, oh my gosh, why am I even doing this? And as soon as the task becomes cumbersome like that, we sort of lose the idea. And that's where calculus takes over. That's where sometimes even common sense takes over. And we say, okay, wait a minute, why would we even bother doing this? So the concession that many of our geometry inclined mathematicians started to make is that both left hand and right hand were always going to be relatively imperfect rectangles. So many people started developing a third technique called the midpoint rectangle that kind of helps, in a very literal way, split the difference. So in question number 3, you'll see the exact same diagram. It's still x squared plus 1, so same old curve. But this time, notice where the marked coordinates are. The marked coordinates are in the in-between tick mark regions, which, as you can probably infer, are exactly halfway. So this first tick mark would be at 0.5. The next x coordinate there is 1.5, then 2.5, and 3.5. So we definitely notice that the x coordinates are not very nice. And as I just mentioned, this is probably making us think, oh gosh, this is going to be like that stupid 8 rectangle thing again. Like, the numbers are going to be so ugly. Why do I even want to bother? But there is a point to this, and I think you'll see why in just a moment. Now, in letter A, the observation is definitely that these x coordinates are not integer values, but rather midpoints between the integer values. So if you're going to make any inference about letter A at all, try to stick the word midpoint in your answer somewhere, because the word midpoint really does clearly define why we marked those points where we did. In letter B, it wants you to find the y coordinates of those marked points, which again, you can easily do by plugging in the coordinates into the original equation. So for example, you can find this x coordinate by plugging 0.5 into the equation and doing 0.5 squared plus 1. Or you can use a graphing calculator and quickly generate a table of values to make your life easier. Obviously, for the sake of expediency, I can do that for you quickly. Or if I'm going too fast, you can go back to the first video in this playlist where I had a quick shot on the screen of my graphing calculator. And you can always look back at that in case you wanted to know where I got these numbers from. But the y coordinates of each of these points are as follows. First one at 0.5 has a y coordinate of 1.25. The next one has a y coordinate of 3.25. The next one has a y-coordinate of 7.25. And the last one has a y-coordinate of 13.25. Now I did arrows just to kind of get those numbers out of the way, and you'll see why as I start to actually draw the rectangles. So in letter C, it says partition the area under the curve into 4 rectangles and let the height of each rectangle be determined by these y-coordinates that we just found. So what that means is if I still want to draw 4 rectangles, then the implied width of each rectangle is still going to be dictated by these tick marks at 1, 2, 3, and 4. But instead of letting the height of each rectangle be dictated by a left or a right edge, I'm going to let each of these points, these dots, serve as the height and kind of split the middle. So here's what I mean, and it might be kind of hard to tell what I'm doing, so I'm going to try to do the first one as clearly as I can, and then hopefully you can kind of pick up on this. If you kind of estimate, and I'm just going to do this with a little bit more of a ruler because I was terribly ashamed of my performance in the previous video. The height of each rectangle is going to be the height or the y-coordinate of each point. So if you notice, as I draw this, I'm making each rectangle touch the tick marks. So in terms of height, in terms of width, apologies, my verbiage is getting a little mixed up here. In terms of width, I'm still making it 1 unit wide. That way I can get the 4 rectangles that I need. But you'll notice that I'm using this point to dictate the height of the rectangle. So instead of the left corner or the right corner of the rectangle touching the curve, now it's kind of like the middle of the rectangle is touching the curve. And again, because I didn't make this perfect, it doesn't quite look like that point is directly in the middle, but that's the fault of my drawing, not the fault of the math. So as you're going through each of these, see if you can kind of follow along with me as I draw each of these heights. Now I started on the right-hand edge just so I could start with a nice big example so that you could see it clearly on the screen. But it doesn't matter where you start. You could actually start from the left and work towards the right, or start from the right and work towards the left. The idea is basically that the integer values on the x-axis are still going to serve as the horizontal boundaries, so to speak, of each of our rectangles. And then we'll use the vertical boundary as the point that we already have the coordinate of. So as I go through each one, and it might get easier to freehand them, you'll just have to decide what's best for you, especially if your drawing skills, like mine, are questionable at best. Then hopefully you can kind of tell that we end up with our 4 rectangles. Now again, if for visuals it helps to shade them, go ahead and shade them in so that they look like 4 more clearly defined regions. And hopefully that will kind of help your eye see 2 important things. First, notice how much more accurate this might end up being. Because we noticed when we did the left Riemann sum, there was a bunch of missing or empty space, and we knew we had underestimates because we knew that each rectangle was going to be way below the curve. And when we did the first video, the right Riemann sum, we had gigantic spaces that went way over the top of the curve. So we had an over approximation because we were including way too much. This one, interestingly, seems to kind of split the difference. For every little spot where it looks like we're going to be a little bit under, there's another similarly sized spot that looks like it's going over. So it's almost as if those 2 pieces are essentially canceling each other out. See if you can notice that for all of the rectangles you drew. Obviously, it's kind of hard when you get down towards this little tiny one, but if you kind of notice that under versus over approximation, you might now be getting a hint about why midpoints, though a little bit tedious, are actually a pretty good method worth considering. Now, of course, comes the actual mathematics. Now's the part where we actually want to find the areas. So we've done up through letter C. in the text. We've gotten the heights of each rectangle. We've partitioned it into 4 spaces. So now I'm on to question letter D, where it says find the area of each rectangle and then find the sum on the interval. So same as always, we'll just do base times height for the area of a rectangle. Base of this little tiny one is 1 times a height of 1.25 is 1.25. The base of the second rectangle is 1. Its height, determined by the y-coordinate, is 3.25. 1 times 3.25 is 3.25. In the third example, or third rectangle, base of 1, height of 7.25, so its area is 7.25. And not surprisingly, the last rectangle has a base of 1, a height of 13.25, for a total area of 13.25. Now, if we quickly find the total of all 4 of those pieces, and again, I'll just do this for you for the sake of expediency, it looks like we get a total area of 25. Now, while that number in isolation doesn't necessarily mean a whole lot, the comparison here is what I think is most valuable. So in letter E, it's asking us to actually compare. How does this area compare to the ones we calculated with a right Riemann sum and a left Riemann sum of varying degrees of closeness? So when you actually compare back, you'll note that the right Riemann sums had areas of 44, 34, and 29.5. Not terrifically accurate, because we knew those were going to be over approximations. And for reference, we did the calculus and realized that the actual true area was 25.333. So not exactly close. I mean, the 8 rectangle picture was the best we could do, but even that was definitely an over approximation compared to our target number, the number that we really wanted. Now, by contrast, take a look at what you got on page 30. And even though I didn't write my answers, hopefully we can quickly just go back and fill them in. If I got the right answers, hopefully, it looks like for the first area, whoops, apologies for the radio silence there, dropped the pencil. The first area with the 2 rectangle sum has an area of 12. The second one that we already did was 18. And the third one was 21.5. All under approximations, because you can tell each picture had that missing space. And again, in contrast, all less than the actual area of 25.333. So worth noting. But perhaps most importantly, compare the midpoint answer that we got, 25, to the actual area from the actual integral, which was 25.333. That is extremely close. So you can tell that the midpoint method was clearly the most accurate of the 3. And the reason probably has to do with the idea that when we made our diagram and noticed that the overestimates and the underestimates kind of canceled each other out, really leads us to a much greater degree of accuracy that the other rectangles simply couldn't afford. Now, of course, the trade-off is midpoints can be tedious to calculate. Obviously, you're dealing with decimals, and in a no calculator situation, this would be a little bit more cumbersome to have to find the y-coordinates by plugging in and doing x squared plus 1 by hand with decimal values. So midpoints are actually not as widely used as you would think because they're not efficient. And remember, the thing about the Riemann sum that we discussed on page 29 is that it's about getting close enough. In the big scheme of things, there's a fair population of mathematicians who say, all right, just do a left Riemann sum. I know it's not going to be perfect, but whatever, close enough. And it seems crazy to think that mathematicians would actually say that, and yet you'll find lots of problems, both in this packet, on AP tests, wherever, that actually ask you for an imperfect answer, knowing it's going to be imperfect, knowing it's going to be just an approximation, because we know it's easier that way. So just to kind of put it all in perspective, and this is what that note at the bottom of page 33 is all about, The idea is basically to try to get a good enough approximation. If they specify what method to use in a question, then we always use that method. If it doesn't specify and you're left to make your own choice about the method, then you're going to have to make a judgment call. Is it better to have a higher degree of accuracy but with a more tedious calculation? Or is it better to do fewer rectangles or a left or right sum for ease of points and know going in that it's not going to be a very accurate answer? So, things to ponder for sure. And as we make the transition from page 31 to the next video for page 32, kind of chew on that idea. And if you have some time, read this little blurb at the bottom and just try to digest the main idea so that when we get to that next page, we can start to sort of put it all together.